So for body one, down at pin A, we have the force negative 250, negative 433. And up at the pin, we have the force on one by B, positive 250, positive 433. And then on the other member, we have the force, so 2B should be, oh yeah, that would be 2C. 2C is negative 250, 433. And up here, this would be positive 250, negative 433. And if you calculated if you used inverse tangent to figure out those angles and compared them to the angles of these members, what you would get is that this member is entirely in tension with a force magnitude of 500 newtons. And the other member is entirely in compression with a force magnitude of 500 newtons. Okay, so why is that? That's not a general fact. It's not always going to work out this way. But what is it about our problem that gave us that? And the answer is, anytime you have a two-force body, they're called. How many forces do you think are probably acting on two-force bodies? E? 2, right. Good, Mike. So two-force bodies, anytime you have these, the loads, the forces, are equal and opposite. And not only that, but they act parallel to the line between the two joints. And the reason that is, so let's just think of some general object, and let's say that there's a force here and a force here. And say that there was a force acting this way. If this is going to satisfy Newton's second law for equilibrium, what direction does the force have to act on the other side? It has to be equal and opposite. But then think about rotational Newton's second law. What's going to happen here? What are these going to do to this object if you have forces applied that way? It's going to rotate it, right? And so there's no way, if you have one force acting out of the line between those two joints, there's no way to make it, put it in equilibrium with only